this chapter, we will be introducing the concept of integration. In this lesson, we will be looking at motion problems.
Hi everybody. Okay, now in this video here we're going to take a look at motion problems. Again, we're going to revisit motion problems. We've looked at this earlier in this course, in this set of videos here. And what we were doing is we were looking at displacement, velocity, and acceleration. And we notice, okay, so remember displacement, oh my goodness, I spelled it wrong, displacement, sorry, displacement, velocity, and acceleration are all functions of time. Okay, they are all functions of time, so the variable t. This is the independent variable when we're doing this work right here. Okay, and this, man, it's so important to remember that. T, this is the independent variable. Now, what we noticed earlier in this course here is that velocity, okay, is equal to the derivative of displacement. Now, and that is the derivative with respect to time. And you're going to see actually in this particular chapter, particularly as we move further through this, that this notation is actually going to become useful, more useful, okay, than we maybe have thought about it in the past here. Now, at the same time, acceleration is the derivative of velocity with respect to time as the independent variable, and that means it's going to be the second derivative of displacement, and that's going to look more like this, the second derivative of displacement with respect to time. Now, in the previous material that we've worked through, we went this direction through the material. We went from velocity, we went from displacement by taking the derivative to get velocity, or we took the derivative to get acceleration, or the second derivative to get acceleration. Now what we're going to do is we're actually going to work the other direction here, okay? We're going to use antiderivatives to start going backwards from velocity to displacement, or from acceleration to velocity, okay? And you're going to see how this relates back to some of the material we've looked in the last couple of lessons here. But yeah, the easiest thing to do, let's just jump in and start doing some examples. All right, so here's our first example here. And actually, this is going to be a really good example. You're going to see something here in this problem that's going to be kind of a recurring procedure that you're going to apply kind of from this point on. It's like, well, I mean, if I was going to compare it, what the sort of the pattern that you're going to see here is kind of like getting a first glimpse of the Pythagorean theorem, and then all of a sudden you see that over and over and over again everywhere you go here. Same sort of thing. You're going to see a pattern here that is going to be applied over and over and over and over. But here it is. Here's the question. The instantaneous velocity of an object moving along a horizontal straight line relative to a fixed point 0, or O, or whatever, is the velocity is 8t minus 5, where t is greater than 0. We want to know what the displacement is from 2 seconds to 5 seconds. Okay? We just want to know, how did this thing move in that time period there? Well, we've got velocity, and so what we need to do with this is we need to get displacement out of that. So remember that velocity is the derivative of displacement with respect to time. And so there's our 8t minus 5. So now, by taking the antiderivative, okay, I can recover the displacement function here. So that's going to be 8t squared over 2 minus 5t. But remember, every time I take an antiderivative, I need to include this arbitrary constant. Even if I'm talking about a word problem here, we're going to see that arbitrary constant is actually really important, okay? Just because it's a word problem doesn't mean I can just ignore it. Ish. And we're going to talk about that a little bit more as we go along here. Now, remember from a previous video here that oftentimes what we'll do is when we get a problem like this, we've got boundary conditions. But the truth is I don't have any boundary conditions here. I don't exactly know what its displacement is at time equal to 0. In fact, I don't really have any indication of that at all. All I'm asking for is what its displacement is between 2 and 5. Now let's just think about that though. If I wanted to know what the displacement was from 2 to 5, if I wanted to know what the change in displacement is, okay, that's going to be the displacement or the second value of displacement minus the first value of the displacement. So this is going to be the displacement at 5 seconds minus the displacement at 2 seconds. Now watch what happens when I do this. And I know at this point in time I don't know what the arbitrary constant is, but watch what happens. Okay? I'm going to take and plug that in. So that's going to be 8. Oh, shoot. I just looked up here and realized I hadn't simplified that, and I can't believe I didn't. That should have been 4t squared minus 5t plus c. Man, I wouldn't let my students get away with that. I can't believe I just put that in there. I started writing that in. I'm going to leave that in there for now, but terrible. This will be minus 5 times 5 plus c. So there's the value at 5 seconds there. Okay? Now what I want to do is I'm going to subtract the value at 2 seconds. And so that is going to be, now here I'll put the 4 there, 2 squared minus 5 times 2 plus c. Now, when you put this all together, this is going to end up becoming 75 plus c. Then we're going to subtract 6 plus c. When that negative goes through, this c is going to be negative, this one's going to be positive, and so when I put those together, they're going to cancel each other out, and I'm simply going to be left with 69 centimeters. Now, you might ask at this point, well, wait a minute. We talked about this before. If you put two arbitrary constants together, shouldn't the result just be an arbitrary constant? And the answer is yes, if they're not necessarily referring to the same formula. If they're not necessarily the same arbitrary constant, then yeah, that's exactly right. But here, this is exactly the same arbitrary constant. We are referring to the exact same expression both times. That c is exactly the same as these two c's there. So they will cancel. In this particular case here, that does work. And it works really well. Isn't that interesting that that arbitrary constant kind of disappears when I'm asking you to compare the value of the function at two different values of the independent variable? I'm going to say that again here. And notice I'm not referring to it as time right now, because I want you to get a broader sense of what's going on here. When I'm given a derivative and I want to find the difference in the value of the function, okay, I take the antiderivative, my arbitrary constant pops out. But if I want to find the difference between the values of those two functions at two different values of the independent variable, that constant disappears. It becomes irrelevant. That's a great question. Really good question. Let's take a look at another one. Okay, so this question tells us that the acceleration is 16 t plus 2 to the negative 2 meters per second squared. And we're supposed to find the velocity if when t is equal to 0, v is equal to 8. Now take a look at that. T is equal to 0, so there's my independent variable, and there's the value of the function here. Now, I realize that's the derivative of displacement, but I'm only asked to go back one derivative to velocity, so that really is the value of the function that I'm looking for. So these two right here form a boundary condition. I can plug those in to find the arbitrary constant. So let's do that. So dv by dt, remember this is my a, my acceleration, this is going to be 16 t plus 2 to the negative 2. Now that means velocity is going to equal, well, let's take a look at this. This really does look like to me an example of the chain rule being used here. But then again, I notice that the derivative of the inside is just 1, and I like that. Okay, that simplifies things down a bit. So what I'm going to do is increase the overall exponent here by 1. But remember, I'm increasing negative 2 by 1. So it's going to go to negative 1. And then I will divide by the new exponent here, negative 1. And I'll add my arbitrary constant. Okay, now I'm just going to double check that that actually works. If I take the derivative of this, I should go right back to this expression up here. So bring down the negative 1 goes to negative 2, like that. Negatives would cancel. I like that. And the derivative of what's inside here was just going to be positive 1. So yeah, that works out good. So my velocity here is simply going to be negative 16 t plus 2 to the negative 1 plus c. Okay? Now, I have enough information, I can actually figure out what that arbitrary constant c is here. Because I know that my velocity is going to be 8 when time is equal to 0 here. And looks like I was trying to write a 2 there. That is my plus sign to the negative 1. So what am I going to get here? Oh, sorry, plus c here. This is going to be 8 is equal to, okay, well this is 0 plus 2 is just 2 to the negative 1 is going to be 1 over 2, so a half of negative 16 is negative 8. Well, that makes it easy. So c is equal to 16. So therefore, I know that my velocity as a function of time is going to be negative 16 t plus 2 to the negative 1 plus 16. And I just take and put the arbitrary constant in. And there you go. Okay, so in this question, we read that the acceleration of a spring-driven model car is initially 20 centimeters per second squared. And it decreases, now this is interesting, at a constant rate of 2 centimeters per second squared per second. So what we're giving you right here is the rate of change of acceleration. Now for those of you that maybe don't know that, when you talk about the derivative of acceleration, it's actually called jerk. So we're giving you the jerk of the system here. As the spring runs down, okay, find the velocity if the car is at rest when t is equal to 0. Now, I'm asking you for velocity, but what I've given you here is the jerk. So I'm actually giving you the derivative of acceleration with respect to time. Now, a couple of things. Now, first of all, notice it decreases at a constant rate, which means this is actually negative 2 centimeters per second squared per second. And then what I want to do is I'm going to use what I know here to go back to acceleration and then go backwards again to velocity. So now we're going to start to string these ideas together. Now, bear in mind the car is initially at rest when t is equal to 0. So this is like one of those cars that you pull back, and you're winding it up, and then you let it go. Okay. So initially, it's got this string. The spring is all wound up, and it's pushing, and it's going to give this thing an initial acceleration. But as the spring starts to expand or whatever, it's still pushing it forward, but pushing it at less and less with less and less force here. So anyway. So the first thing we're going to do here is we're going to take the antiderivative of this to get acceleration. And when you take the antiderivative of a constant, that's just going to be negative 2t plus c. Okay? But we were given some boundary condition information here. Now, don't get confused. The boundary condition information we're referring to here is not the velocity of the car is 0 when time is 0. Okay? That's because I'm looking at acceleration right here. But I did tell you that initially, and remember initially means time is equal to 0, the acceleration is 20 centimeters per second squared. So I know that this is going to be 20 when t is equal to 0. And that makes this calculation really easy. That means at this stage right here, that arbitrary constant is going to be 20. So therefore, my acceleration is going to be negative 2t plus 20. Awesome. Except that wasn't what I was asking you for. I was asking for the velocity. So now what I got to do here is remember that, oh, well, that's the derivative of velocity, that acceleration I just figured out here. So that's going to be negative 2t plus 20. Now I want to do this process again. So negative 2t, I'm going to increase the exponent by 1, divide by the new exponent. 20t, okay, to go from constant to linear. So I went from linear to quadratic, constant to linear, and then I have to add my arbitrary constant. And now these are not the same constant. In a previous question, I was working with the same expression, and my c's would cancel here. This isn't that same issue going on. This constant popped out of this bit of work here when I took this antiderivative. This is a new antiderivative, so this is a new arbitrary constant. And I will simplify this by making it negative t squared plus 20t plus c. Now, I can do a little bit better here because I am given some information here. I'm told that initially this is at the function here is at rest, or the car here is at rest. So its velocity is 0 when time is equal to 0. Now, that's a whole lot of canceling that goes on here. And actually what I'm getting immediately is just that c is equal to 0. That's okay. Okay, that is okay. I know that sometimes when you get a result like that, it tends to throw people off. They think they're doing it wrong. But that's totally fine here. So what that means is up here, therefore, my velocity is simply going to be negative t squared plus 20t. Okay, with a 0 at the end. All right, let's do one more word problem here. And actually, I believe we have saved the best one for the last here. I love this problem here, mostly because as we start to get through this, if you've taken some physics before, you're gonna see something here, and I'm hoping that you like it. Okay, so a stone is thrown vertically upward from a point 1.5 meters above the ground with an initial velocity of 10 meters per second. So bear in mind what's going on here, what that is just said, without even reading what the question's asking. When t is equal to 0, this stone is 1.5 meters above the ground, and it's got a velocity, positive velocity, of 10 meters per second. Okay, so basically I'm giving you some initial conditions here, and at this point here, that should probably be enough to clue you in that I'm giving you some boundary conditions here. Now the question is asking, determine when the stone hits the ground. When the stone hits the ground here. Okay, well, you might think here and start, well, I'm just going to start with my velocity and go backwards to my displacement here. But the problem with that is that you're missing some information. We've thrown this thing upward. Now, we're interested in where the stone hits the ground. If you were to find the antiderivative of this right here, just this expression right here, you'd get 10t. Now, that would tend to indicate that its velocity is just increasing every second. And that's not what you experience. When you throw a rock in the air, it goes up, slows down, and then speeds up again and comes down and hits the ground. That's your experience. So in order for me to get an accurate image of what's going on here, I need to incorporate acceleration. Okay? Now, that's where we're going to start. So we're going to start with acceleration. Well, you might look at this problem and kind of depending on your background with this, you might look at this and say, whoa, time out. There's no information given about the acceleration. Yeah, but there it kind of is. When you throw something in the air, it always has the same acceleration. Okay? The Earth is always acting on it, and the objects are always accelerating towards the Earth with the same rate of acceleration. And the symbol that we give to that is g. Now, we know that g is going to equal negative 9.81 meters per second squared. Okay? That's just the value of the acceleration on any object that's any projectile motion here. So that's actually where we can start. So now I know that my derivative of velocity is going to equal the constant g. Now, I could write negative 9.81 over and over again, but I'd rather just use the letter g. And I think most people are going to be with me on that they'll understand what's going on here. So now, when I take the antiderivative, I'm going to get gt plus c. Okay? gt plus c. Now, even right now, some of you should start to look at that and go, hey, wait a minute. Let me go on here and let's do just a little bit more here. I have some initial boundary conditions up here that should help me figure out what's going on here. I know that initially, when time is equal to 0, my velocity is 10. Okay, positive 10 too. Positive because it's going up. Well, 0 times g is just going to be 0, so that means c is going to equal 10. And so as a result, my velocity is going to look like this. That's going to be gt plus 10. Now, let me just write something next to this here. Bear in mind that that 10 is my initial velocity, right? And that my g here is referring to the acceleration in this particular system, which in this case is acceleration due to gravity. Well, what that means is that my velocity here, if I change my symbol a little bit, instead of using a g, I'll just use the letter a for acceleration. T plus the initial velocity. Oh, do you recognize that particular equation? Yeah. Yeah, that's like a kinematic equation. Okay, you would have worked with that one in your physics class. Anyway, let's keep going here, because this isn't where that we wanted to end here. The question was, determine when the stone hits the ground. When the stone hits the ground, and for some people this is really hard to get your head wrapped around here. For when the stone hits the ground, okay, that's where the displacement is equal to 0. That's how I determine, okay, when it asks when, I'm going to set my displacement equal to 0 and solve for time. Now, sometimes people get confused and they think that velocity is equal to 0 when you hit the ground. And I've seen a lot of people do that. And that's not true. Velocity becomes 0 when it hits the ground. But at the instant something hits the ground, it can have quite a bit of velocity. In fact, that's why it hurts if you're the one that's hitting the ground. Okay? If your velocity just became 0 when you hit the ground, it would never hurt to fall off of anything. But it does, okay? So the bit of information you need is this right here, that the displacement goes to 0. Now, which means that I need to take this expression right here, and I need to go back another step to displacement. Okay, so what I had there, just to rewrite that, I had v is equal to gt plus 10. So now I know that v is the derivative of displacement. So that's going to be gt plus 10. And now I'll integrate that, or I'll find the antiderivative. So here this is a linear, and when I find the antiderivative, I'm going to increase the exponent by 1, divide by the new exponent, so gt squared over 2. This is going to become 10t, and then I'm going to introduce a new arbitrary constant. Now, I can figure that out easily enough, though, because I know what some of my initial information was. I know that when time is equal to 0, my displacement was equal to 1.5. That was one of those bits of information that I was given initially here. So I can use that to determine that the value of the arbitrary constant here is 1.5. So up here I can write, okay, so my displacement is going to equal gt squared over 2 plus 10t plus 1.5. Now, again, I can't resist just showing you this. Let's go back here. This means my displacement is equal to, well, let's get rid of the g again. Let's just call it a to represent acceleration, kind of in general. At squared over 2. Remember that the 10 here was our initial velocity times time. And notice that the 1.5, I got that by plugging in the time is equal to 0. So this is my initial displacement as well. And do you recognize that function? Isn't that neat how these kinematic equations just pop out of calculus? Oh, I just love this stuff. Okay, so the last thing that we got to do here is we got to figure out now, or we want to figure out now, when this particular object, or this stone I should say, hits the ground. So what we're going to do now is we're going to let our displacement go to 0 in this function. So 0 is going to equal gt squared over 2 plus 10t plus 1.5. Okay, well, you might not like where this is going, but turns out you're not going to be able to factor this really nicely. So you're going to have to use the quadratic formula to solve this. So t has got to equal negative 10 plus or minus the square root of 10 squared minus 4 times g over 2 multiplied by 1.5 all over, what is that, g over 2. Now, bear in mind, in this particular context here, okay, bear in mind that g is going to equal negative 9.81 meters per second squared. Negative, whoops, sorry, you can't see that. Negative 9.81. So when I plug that in for g here and g here, it's this number that I'm using. However, I do think that when I did this did this calculation initially, because I'm looking off of a slightly older resource here for this question, I believe I just used negative 9.8. But in either case here, what you're going to get is something that looks like either time is equal to 2.2 seconds or time is equal to negative 0.1 seconds. Well, now clearly this one doesn't make any sense. Okay? Clearly this one doesn't make any sense because we know that that object doesn't follow the parabola prior to it becoming a projectile. Okay, so negative time really doesn't make any sense here. And so our answer, therefore, is that it hits the ground at 2.2 seconds. That's what we were looking for. This is a great question. And you're going to see as you go on, if you go on with mathematics here, that there's all sorts of places here where some of these physical rules are really held in the mathematics of the problem.